Having discussed the basics of operational amplifiers, we continue to study them. For example, how they can be used and what are their circuit applications. First, we take op amps in open loop. By open loop, we mean that there is no feedback involved in it. That means that is op amp without feedback. Op amp without feedback network. How will it behave? Just let us consider a op amp with the two inputs as we have said. So, let us take that in open loop this is non-inverting input to which we apply a input signal and let this inverting input be grounded. Now, this A is the open loop voltage gain and V out we take from here RL and this is V out. Now, this A is the open loop gain, always remember open loop gain. Gain of the op amp, and the 741 op amp, 741 which is a general purpose op amp and that we are taking as the model, just sample to be used. So, this 741 has A around 10 to the power 5, 100,000 is the voltage gain. Now, let us see what will happen if we apply a, for example, a positive signal Vi is plus 1 millivolt. Let us say this is DC. Now, mathematically what will be the output? Output is gain into input, that is this V out will be A into Vi. Gain is 10 to the power 5, 10 to the power 5 and this is 1 millivolt. So, 1 is to 10 to power minus 3 volt. So, the simple mathematics says that V out will be 100 volts. Now, very fundamental thing that in a circuit this V out, the output voltage cannot exceed the maximum DC voltages available or applied to the circuit. Therefore, this instead of 100 it will saturate at V set. Output V out, that is output, will saturate at plus V set and V set normally will be slightly low, but of the order of VCC. If VCC is 15 volts, then plus V set will be roughly 14 or 14.5 volts. So, it will saturate. So, what we will get with the non-inverting signal, the output will be like this. this is time, this is voltage, and this is V set. This is minus V set. So, if the voltage is positive, it will just saturate here, and if it is negative voltage here, if this voltage is negative, then without change of polarity it will appear in output and it will saturate here. Now, if we apply a sinusoidal signal, let V I be sinusoidal like this. This is the input signal, and if this is say of the order of a millivolt, then same thing will happen. Here it will just saturate at plus V set, and here it will saturate at minus V set. So, if this is the input, the output will be this. This is the output voltage, time plus V set, and here this is minus V set. This is highly distorted. This is not the replica of the input. Therefore, thus in open loop, a op-amp amplifier is rarely used, almost never used as an amplifier, because output will be a kind of a square wave for a sinusoidal signal, and so this is highly distorted when we compare the two. The same thing will happen when we apply the input instead of the non-inverting input. If we apply at the inverting input, all voltages are always with respect to ground. When we say Vi, this is like this actually. Here this is the ground level and this is grounded, and here we apply a voltage. This is the inverting input and Vi, and this is the output, which is again with respect to ground. This is V out and this is the load. So, this is not shown, but in a statement we cover it that all voltages, output and input voltages are with respect to ground. So, here when we apply it, the sign will be inverted. If it is DC, if we apply a positive voltage, it will saturate at minus V set, and if it is negative voltage, it will saturate at plus V set. And if we apply a sinusoidal signal, and if this exceeds the limit A into Vi more than Vcc, then it will produce a signal at output, a square wave with inversion. That means thus it will be like this. This is time, this is minus V set plus V set, and this is voltage. So, this is, and if we apply, use it as a differential amplifier, then the difference of the two will be will appear, which will again normally it will saturate, unless the difference is in say microvolts. then of course amplified signal will appear. Now, how we summarize this? That normally as an amplifier in open loop op amps are not used. Sometimes they can be used as comparators. Open loop op amps are used as comparators. Comparator is a circuit which compares two voltages. So, here for example, we give here a one is the reference, this is a reference voltage and this is the applied voltage V applied to be compared. Applied means the one which we want to compare. Now, the output when we take then as soon as this will exceed this, the output will saturate accordingly and signal will be available. So, this way the three configurations in open loop, the inverting amplifier, non-inverting amplifier and as a difference amplifier, this is not used as an amplifier, but one of the applications for open loop is as comparators, where V0 will be A, V, I, D and A into V1 and V2, where one of these can be a reference voltage. So, this can be used as an comparator. But the use of op amps as an amplifier is very wide, very wide. As I said, there are a large number of applications of op amps, but most of these applications are with the using proper feedback. And the amplifier realization, that is construction of an amplifier, is simplest with a op amp. We can choose how much gain, you will see we are coming to that, we can choose how much gain for the amplifier is required and what is the input impedance we want. Then we have to choose just 2 or 3 resistances of an appropriate value. They are to be attached with the op amp and the design will be extremely simple. You need not to bother about biasing network, this and that. That is all, everything has been taken care of by the manufacturer in designing the op amp. So, we take the applications of op amps as amplifier first. So, op amp as amplifier. Op amps as amplifiers. There are 3 amplifiers and all 3 we will take one by one. First we take non-inverting amplifier, non-inverting amplifier with feedback, and this feedback is negative feedback. In amplifiers we always use negative feedback. This point was stated and made clear when we were discussing feedback in amplifiers. Negative feedback. First let us see what will be the simple circuit. and then we analyze this amplifier. This is V out, and this is the input, and the feedback is this RF, this resistance is RF, and this is R1. Look at the simplicity of the circuit, and of course these sources are there, plus VCC and minus VEE. Even if we do not show these two DC supplies, it hardly matters. It is implied no electronic circuit will work without a DC supply, because DC voltages are needed for biasing the transistors, which is so important. Biasing is so important for the operation of any transistor. So, this is the circuit, and this we analyze, and since the input signal has been connected with the non-inverting input, which is indicated by plus sign. So, this is a non-inverting amplifier with the proper feedback. Now, we analyze it, and remember A, many times written here, A is the open loop gain, gain without feedback. This is the feedback amplifier. How much will be the gain, that we will estimate and evaluate for this, but this is provided by the manufacturer, open loop gain. And for most of the amplifiers, particularly 741, this is A is 100,000, 10 to the power 5. Now, the V out, these we identify, this is V1 and this is V2. Now, V out, this V out, simply this is gain and the difference of two voltages, V1 minus V2. Whatever is the voltage here, that is V1, and whatever is the voltage here, that is V2. So, the difference of this will be multiplied with the gain, will be the output. If we take in this figure, in the figure V1, this V1 is equal to Vi. These two are identical. So, V1 is Vi, and V2 will be the voltage here, fed back voltage. This is, we write Vf. Vf is voltage fed back to inverting input, and this is simple. This we have talked several times, that, but anyway I do this. Voltage here is V0, and these are two resistances, and what will be the voltage drop here? This is a voltage divider circuit, which I can draw like this actually. This is RF, R1, and whatever is the voltage drop here, this is VF, the feedback voltage, and this is V0. See here, V0, and this resistance, these two resistances, they are dividing this voltage. So, this is the network. The how much will be Vf? The current will be V0 R1 plus Rf. This is the current through these resistances which are in series, and the voltage drop across R1 will be the current. This is the current actually. This is the current, and multiplied with R1 becomes the voltage. So, Vf is R1 plus Rf V0. Simple voltage divider circuit, and this we have talked several times. This is the current which will be flowing, and what will be the voltage drop across this multiplied with R1, that is this voltage Vf. So, we substitute the value of V1, substituting the values of V1 and V2. This Vf, this is equal to V2. The voltage here with respect to ground is the same as voltage Vf. So, this is V2, and V1 we already have this. So, when we substitute V1 and V2, we get V0 is A V1, V1 was Vi minus V2, V2 is this. So, R1 plus Rf into V0. So, this is simply V0 equal to A into V1 minus V2. We have substituted the values of V1 and V2, and this we can write, or we take this term here, or V0 is V0 into 1 plus AR1 R1 plus Rf. This is AVI. Let us or a cross multiplication will give A0 R1 plus Rf plus A R1. This is equal to AVI R1 plus Rf. And now from here we can get the closed loop gain. From this expression we will get A with feedback. So, normally we write with F or even FB with feedback. Gain with feedback. That is AF is closed loop gain. Closed loop gain. This is equal to V0 by Vi. Here input signal was Vi, output V0. So, ratio of output voltage to input voltage is the gain. This is the op amp in open loop and this is the feedback network. So, this whole amplifier is a op amp with feedback. This is op amp with feedback. For that, this is the gain, and which from this equation V0 by Vi, this becomes equal to A R1 plus Rf, R1 plus Rf plus A R1. This is the exact expression. We write here exact. This is the exact expression for the voltage gain. But when we see the practical situation, it gets drastically simplified. And the situation is that normally, and normally means most of the time, A R1 is very large as compared to A R AR1 is very large as compared to R1 plus RF. R1 into A is 10 to power 5, 10 to power 5. So, 100,000 times R1, while these resistances may differ hardly by a factor of 2 or 3 or 5. So, this condition will be mostly available and applicable. So, this can be neglected, and then gain with feedback becomes equal to A R1 plus Rf by A R1, or simply 1 plus Rf by R1. This is the gain of the non-inverting amplifier with feedback is 1 plus Rf by R1. How simple! You choose the gain, how much you want, 10, 20, 30, 50, 100. Accordingly, choose these two resistances. If, for example, now because this is a op amp is a small signal device, so resistances normally will be in kilo ohms, because ratios, suppose we want a gain of 20, let AF be desired is 20, and for that, from this expression we want Rf by R1 ratio to be 19. Now 19 you can have, for example, Rf you can choose say 190 into 2, so many ohms, and R1, because this is to be 20, this ratio has to be 20. So, this becomes 380 divided by 20. So, 20 ohms and 380 ohms if you take, ratio will be 19, but these resistances will draw a large current, and the currents will exceed the maximum current which is recommended for the op amp, and op amp will burn. So, instead of in ohms, these are taken in kilo ohms. So, we can choose these in kilo ohms, and we can have this ratio 19, then gain will be 20. For example, let RF be 19 kilo ohms and R1 be 1 kilo ohm, then gain AFB will be 1 plus 19 K by 1 K. So this is 20, gain will be 20. How simple it is to construct a non-inverting amplifier with a desired gain. Now let us go further to show that non-inverting amplifier with op-amp is very close to an ideal voltage amplifier. It is an ideal voltage amplifier, and this we can show by using the concepts of feedback. Now from this equation, V2 equal to Vf, which was equal to voltage divider R1 plus Rf into V0. This is Vf. You remember that in the feedback networks 1 plus AB, where AB is the closed loop gain and beta is a factor, and so beta is Vf by V0, the fraction which is returned to the, this is the input of this is the feedback network. The input here was V0. This V0 is the input to the feedback network and output we are taking here. So the gain of feedback network is output divided by input, Vf by V0, which from here we write as R1 by R1 plus Rf. This is the gain of the feedback network, and then using this expression, using R1 plus Rf equal to B in the AFB exact equation, which was A R1 plus Rf, R1 plus Rf plus A R1. If we use this, then this can be written as AFB is A1 plus AB. Just substitute like this, and this becomes this. We divide by Rf actually, so this is A by 1 plus A R1 plus Rf, which this is B, so this is this expression, which was the expression for a voltage amplifier with the negative feedback. And this term AB will be very large in comparison to 1. So 1 can be dropped. So the gain AFB is 1 by B, and that is highly stable. The gain of the feedback amplifier op-amp does not depend on variations in A, which may vary because of aging or temperature or noise in the surroundings, whatever may be the reasons. But the gain of the feedback amplifier, the non-inverting operational amplifier with feedback, is stable and it simply depends on the B. The in B network is normally few resistances. So with this expression, every quantity will vary with the, you remember we said this with feedback, that because the gain is A 1 plus AB, then all quantities will vary, either increase or decrease by a factor 1 plus AB. If they increase, we will have to multiply by this factor, and if they fall, we will have to divide it. So this is this here, and the sacrifice what we are doing, the gain falls from A to this. The gain of the non-inverting op-amp with feedback is much reduced. It is reduced by this factor 1 plus AB, and this factor may be 100. So then the gain will fall by 100, 10 to the power 5 by 100, or even 1000. So if it is 1000, this factor is 1000, it will be just 100, maybe less. So now what are the quantities? We recollect from our discussion in the feedback chapter which we finished, that input impedance with feedback, that is RIF, F with feedback, this is Ri and it increases by this factor. If this is Ri is the input without feedback, then this is the input impedance. It will increase by this factor, and this factor is, for example, often 1000 and more. So 1000 times the input impedance will increase, and the output impedance in this case will be reduced. The output impedance is reduced and with feedback of F. If without feedback it is Ro, then this is 1 plus AB. It will be reduced, and a ideal, or rather a good voltage amplifier is supposed to have high input impedance and low output impedance, and bandwidth will increase, because you will recall that gain bandwidth product is constant. Gain, voltage gain into bandwidth product is a constant for a device. In this case, gain falls by a factor 1 plus AB, and hence the bandwidth increase by the same factor 1 plus AB. So with feedback, bandwidth with feedback, this is, if this is the bandwidth without feedback, then it will be, this is bandwidth without feedback. So we are seeing all through that non-inverting op-amp is a non-inverting op-amp is an ideal voltage amplifier. Non-inverting input op-amp, which is called actually non-inverting op-amp, is an ideal voltage amplifier. So this is the major things about a non-inverting amplifier. Next, we take a inverting amplifier, and how we know that whether the amplifier is inverting or non-inverting? Simple, where we are feeding the input signal. As you have seen in this case, the which we have studied, the input signal was attached to a non-inverting amplifier, non-inverting input. So it was a non-inverting amplifier. Next is inverting amplifier. Inverting amplifier with feedback. Let us see the circuit. The circuit is this. This is the circuit for inverting amplifier. Just we connect two resistances RF and R1. These two resistances externally connected, then it makes a inverting amplifier. And now we investigate the important properties of this circuit. Here RF, this is the feedback resistance, feedback resistor, and R1 is another resistance, and we can see that this is the voltage shunt. Voltage shunt feedback circuit. Now, the most important property of an amplifier is the voltage gain. The other important property is input impedance, and so on. So, first we take a voltage gain of this amplifier. Let us see here, this current is II, this is IB, and this is IF. This is the input current, which is divided into two parts. So obviously summation of currents at this point, which is V2, and this is V1, this is of course is 0 because it has been grounded. This terminal is at potential V2, and this is with respect to ground of course, and this is at V1, but V1 is 0. So summing up currents at V2 gives II, this is equal to IB plus IF, and IB, you remember that the input impedance of the op-amp is extremely large, it is in megohms. So this current is very feeble. So since IB is very close to 0 because the input impedance of the amplifier is very high. Therefore, II is simply equal to IF. Now, what is the value of II? In this terminal, one terminal is at the voltage Vi, the other terminal as V2. So, what is the current flowing through this? Simple Ohm's law, potential difference is Vi minus V2 divided by R1. So, this is this current. This is Vi minus V2 by R1. This is equal to IF, and in IF the two terminals of IF, one is at voltage V2, other is at voltage V0, output voltage. So, this is equal to V2 minus V0 by RF. And from here we can, what will be the gain of the amplifier? This is equal to V0 and two voltages V1 by V2, but V1 is 0 because it is grounded. V1 is 0. So, since V1 is 0, A is V0 by V2, and of course there is a minus sign here. From here V2 is equal to minus V0 by A, and this we substitute. Let us call this equation X. In this equation we substitute this, substituting for V2 in equation X, we get Vi minus V2, but because V2 is minus V0 by A, so this is V0 by A by R1. This is equal to minus V0 by A minus V0 by RF, or the voltage gain with feedback. This is equal to V0 by Vi. Output is V0, input is Vi. So, this is the voltage gain of the total amplifier, and this is equal to minus ARF. Just from here it is simple manipulation, and this is R1 plus RF plus AR1. And since AR1 is very large as compared to R1 plus RF, so this we can drop, and AFB gain with feedback, this simply is minus RF by R1. How simple it is. The expression for the gain of this inverting amplifier, this of course sign shows the inversion as it is, we expect it because it is a inverted input, so inverting input, so hence this sign indicates that, and just choose the desired ratio RF R1 required to obtain the the desired gain. If gain has to be 100, choose this 100k, this as 1k, the gain will be 100. How simple it is. You cannot think any simpler amplifier in which you choose the gain, several parameters you will have to adjust and several parameters you have to calculate. Here simply two resistances you have to take of appropriate value, RF and IRI, and this will be the case. So, this is the practical, this is the exact expression for the voltage gain, which is rarely used because it does not make sense while this condition is very much satisfied. Hence, this is the practical expression. So, practical expression for the voltage gain. Now, one very important parameter about this amplifier, and that is this expression can be obtained from this equation if we substitute V2 equal to 0. The same expression which we have arrived here, we get if we substitute V2 equal to 0 in equation X, then we will get the same. Here this equation X was this, Vi is V2 R1 V2 V0 RF, and from here if we substitute this as 0, this is 0, this is 0, then the gain AFB is equal to minus RF by R1. Same expression which here we have obtained above, that is here we got the same thing with this consideration, but the same expression we get with V2 equal to 0. What is V2 equal to 0? This is V2. V2 equal to 0 means that V2 is at the ground potential. It is called virtual ground. The inverting input, very important, inverting input is virtual ground. Virtual ground. Why ground? Because it is at ground potential. And why virtual? Because actual ground can take almost any amount of current, 100,000 amperes, whatever. But here only milliamperes can be absorbed in the device. So, it is virtual ground. This concept, remember that inverting input is a virtual ground, it is at ground potential. This is a great help in simplifying the analysis of more involved circuits like summing, integrator, differentiator, which we are going to study. So, remember two things. The gain of the inverting amplifier is just the ratio RF and R1. Choose these appropriate values for the desired gain, and the inverting input is a virtual ground, and we will continue our discussion. This is a very important point to remember, that inverting input is a virtual ground, it is at ground potential.